In the last video, we saw that the unique solution for this homogeneous system with initial conditions given by x naught is x naught multiplied by this exponential. Oh, by the way, I think somewhere in the last video I wrote x naught e to the at. That's not defined, actually. That's going the wrong direction. The matrix product doesn't even make sense. So that was embarrassingly bad. Don't ever write that. You have to put the matrix on the left side of the vector, the column vector, when you do that multiplication. Sorry about that. Anyways, so then the question is, okay, so if this matrix exponential is so darn cool, how do we find it? Because nobody wants to mess around trying to compute that power series definition by hand and see what it converges to and whatever else, right? But it turns out that we actually have a great, very indirect way to find it that uses existence and uniqueness of solutions for differential equations. So it turns out that the unique fundamental matrix, remember, a fundamental matrix a fundamental matrix for a system is not necessarily unique at all, because it's just a matrix formed by any n linearly independent solutions, right? So for instance, you could scalar multiply a column by something and you'd still have another fundamental matrix, right? So the unique fundamental matrix actually, let me not write that. For the matrix system x prime equals ax, that satisfies having initial condition equal to the identity is xt times x inverse at 0. And this works for any fundamental matrix x. And so with that in mind, we have that the what we call the transition matrix, so x0, so this matrix exponential can be defined by this formula. And so this is actually a well-defined definition by existence and uniqueness. So when we look at this one, what do we see? Well, first off, oh, I forgot to give you the name for this thing. Sorry. So this is e to the at is the transition matrix. For x prime equal ax. Based at 0. Okay, and so the reason why this works is that we have d dt e to the at equals a e to the at. So all of the column vectors or columns of e to the at are solutions of this system. And clearly we have that if you take e to the at and you evaluate at t equals 0, you definitely get the identity matrix. Meanwhile, X satisfies this matrix equation because it satisfies it for each column individually, right? If you remember that X looks like, so here we've got these, bits and pieces of the, we've got the parts of the fundamental solution set in here as columns. When you do this matrix multiplication, like A times X, the way this works, let me recopy this here. Whoops, I got more than I bargained for. Okay, when you do the matrix product here with A, this row right here multiplying against this row right here keeps everything together, right? So this when we do this to find what happens here, and then we multiply with this one times this column again to find out what goes here, and so on and so forth. The data from these other columns don't get involved until you go to compute what happens in these other columns here. And so this is what I mean by it satisfies this identity column-wise. And then also, if we take xt, x inverse 0, and we evaluate it when t equals 0, then this just looks like x of 0 times x inverse of 0, and a function times, or a matrix times its own inverse is going to definitely give you the identity. So by existence and uniqueness of solutions for systems, these have to be the same thing. So the neat idea here is that multiplying by e to the at evolves the system forward in time. Forward by t. So if you have some maybe complicated system, let's just look at a simple system like a 2x2 system, and suppose you're doing population models and you've got a pair of differential equations that are modeling your population of rabbits and your population of foxes, right? And so your rabbits are starting to grow, so then as a consequence the population of foxes starts to grow because there's lots of food for them to eat, right? And so there you are up at some time t, right? And so then you multiply your current vectors. So actually, you know what, let's call this t naught. Okay, so we're looking at the system where we've got x1 at time t naught, and we've got x2 at time t naught, the populations of our animal species, right? And now if we multiply this thing by e to the as, say, and the width of this interval here is s, so out here we're at t naught plus s, then what's going to happen is this matrix is going to evolve all of these systems simultaneously. So now the rabbits are, troubled by the fact that there's so many foxes, and their numbers begin to die off. And so as this happens, the population of foxes begins to slow down because they're having trouble finding more food. So the rabbits are dying and their numbers are plummeting. And then the foxes suddenly begin to starve as well. And now there's less foxes. So the rabbits begin to make a comeback, and the foxes are continuing to struggle to find rabbits. And now we have our new set of coordinates right here. And so we've got x1 at t naught plus s, and x2 at t naught plus s. And that whole drama of all these interacting systems and what they do over the course of those trajectories, that's all built into multiplication by this transition matrix. And then you can do it again, because now you want to know what happens out here at some r minutes later, years later. So here you are at t naught plus s plus r, and so you multiply by e to the ar, and it's going to evolve things forward in time some more, and so on and so forth. Anyway, so that's the transition matrix. There's a lot of information cooked into it.